great.
Okay.
So this is recorded, so everybody else, if you can, mute yourself, then the recording will be better. The sound will be better. Yeah. Thank
Yeah,
you.
and Pencheng, instead of waving, maybe say something, because I'll put I'll put the small icons, so
What
you
do?
don't speak, you won't show up.
Okay, what do? I'll watch you. Yes. Yeah. Thank you. Yeah.
Okay, so I'll start then. So what I would like to report to you guys is some progress that we made in realistic calculations, in particular of iron selenium. So we included, I'll explain that a little better, screen Fock exchange and Hund's metal correlations in our ab initio simulations, and we got a very nice agreement with experiments of several quantities. So let me just jump directly. Okay, these are my collaborators. Tommaso Gorni, this is really the work of Tommaso Gorni mainly. So he's a postdoc in my group in ESPCI Paris, and he's really an expert in DFT and also now with slave spins, including correlation series calculations, and he's done a great work in comparing with experiments. Pablo Villararibi was a PhD student in my group until a couple of years ago, and if time allows, I'm reporting some of his work, but he's also participated to the work of Tommaso. And my collaborator Michele Casula is also here in Paris, and I guess you all know him. So we've done this work together, and it's on the archive, Struggling with PRL. So you'll see here the reference all over the talk. So I'll be talking about iron selenium. Of course, this is not a crowd that needs introduction but I'll just focus on a couple of aspects. So iron selenium, it's slightly atypical among the iron-based superconductors because it's the simplest one. And in the phase diagram, it doesn't have magnetism, but like the other ones, it has an orthorhombic distortion at low temperatures, and in which superconductivity arises. I'll focus mainly on the tetragonal high temperature phase, but then we'll also say something about the superconducting phase, and in particular, what you see here, I'll focus on the fact that the superconductivity, the TC for superconductivity almost quadruples under pressure. So the basic blocks of all the iron-based superconductors, as you know, are the same, are this buckled plane of iron on a square lattice and ligands above and below. And iron selenium has done all of that, whereas the other families has some charge reservoirs in between. The symmetry is always tetragonal or orthorhombic in most of the cases, and the itinerant electrons approaches that we can use to try to model and understand these materials through DFT, for instance, give the correct Fermi surface topology. That is that of a compensated semi-metal with hole pockets in the center of the brilliant zone and electron pockets on the sides. These pockets are formed mainly from 5 bands of main iron 3D character that disperse 4 to 5 electron volts, and with some partially lifted degeneracy that make that all of them participate to the low energy excitations, and they host 6 electrons in the parent compounds, and then one can dope. The nesting of these pockets provides a natural mechanism for the magnetic phases that one finds, and also a natural spin fluctuation mechanism for pairing, which is probably the mainstream scenario for superconductivity. However, we'll see that there are some difficulties in modeling that we'll try to face. So to tackle. So this is the ARPES of the normal phase in iron selenium in the tetragonal phase along the gamma M cut. I'm quoting this ARPES from this group, but there's been a lot of work, and of course consensus has taken some time to rise. I guess we can discuss the details of this, but I'll refer to this scheme of bands in the gamma M cuts, and in particular to the fact that XY band at gamma is sunk, and that seems to be there seems to be an erasing consensus on this, and on the other hand, all the 3T2G orbitals participate to the bands in the cutting the Fermi level at the endpoints. And I will also focus on the topology of the, on the sides of the pockets of the Fermi surface. So I will use these two schemes and refer mainly to these ARPES experiments in the following. So the main thing to be understood right away is that although DFT gives the right topology, it by no means gives the right bands. So here we're just putting any calculation that you can do. PB is GGA, but it could be LDA. Bands are way too dispersive. Even if they cut as say the topology of the Fermi surface is not wrong, but the sizes of the pockets are quite wrong in almost all iron-based superconductors, and for sure the bands are way too dispersive. And you see that you have to renormalize iron selenium by a factor maybe 5 to 6 to get something in the ballpark of what you see in the experiments. In general, the purely itinerant model has problems which are, again, this DFT bands too dispersive. In many compounds, it's 2 to 3 times. In most correlated compounds, is even more. The ordered magnetic moments are unusually overestimated by LSDA. Here are the experiments. Here are the LSDA estimates, and not always the high TC compounds have this nesting properties, and sometimes the low TC compounds do have it. So it's clear that electronic correlations should be taken into account, dynamic electronic correlations, which are missing in the purely itinerant model. And also there is a direct evidence from X-ray emission spectroscopy of local moments in the paramagnetic phase. So how do we introduce this? Well, we use a multi-orbital Hubbard model in which you have a one body part coming from density functional theory, and an interaction that includes intra-orbital, inter-orbital interactions for both opposite and parallel spins. And the difference between the inter-orbital interactions among them and compared to the intra-orbital interaction is embodied by these parameters that is the Hund's coupling. That is a fraction of the Coulomb repulsion, the local Coulomb repulsion, and is the one that gives rise to the well-known Hund's rules in isolated atoms. Now, the fact that these Hund's rules are very relevant for conduction electrons in the localized states, it came as a surprise in the last years. And I would just want to play a little game by showing how non-trivial things are. What I'll show here are simplified model facts, but these are well known. I'm plotting the quasi-particle weight as a function of the interaction strength for several models that you can imagine. So take a certain number of independent bands in which you have only then an intra band local interaction that I call U intra. Then at some interaction strength, your quasi-particle weight will go to 0 and you'll have a multi-insulator. Now, imagine that you turn on the inter-orbital interaction. So the bands don't talk to each other than with this inter-orbital interaction, both for parallel and anti-parallel spins. Well, so you seemingly have more interaction, but on the other hand, you'll have a multi-insulator at a much higher critical interaction strength. So at the critical interaction strength where you had a multi-insulator for bands that were not interacting with each other, when they start repelling with the interband, inter-orbital mechanism, they get more metallic, and you need more interaction to get a multi-insulator. Now, imagine that you reduce, as we do with Hund's coupling, these two terms, inter-orbitals, in this way. Well, now you have U critical for the mod transition at a much smaller interaction strength. So it's really non-intuitive And this is because it's not just the balance between you and the hopping that plays. It's more complicated. It's really the degeneracy of the local ground state versus the active hopping channels that tunes the kinetic energy and then the Euclidean. But okay, this is just a little scheme just to show how things are non-intuitive. And this was for half filling. Now, imagine that you go out of half filling, it's even more complicated. And in fact, even if, as we saw, the Hund's coupling generally correlates and reduces the quasi-particle weights, it also pushes away the Mott transition out of half filling, so that you actually tend to have, for the quasi-particle weight, quite long plateaus in which you have strong correlations, but far from the Mott insulator. And this gives really a ballpark to strong correlations, because you don't need to be close to a Mott insulator to have them. And that's why they're encountered so easily in many materials which are in this situation. So where Hund's coupling is at play and you are off half filling, but not too far from half filling. Now, I'm showing here some DMFT and some slave spin results just to show that they are qualitatively always in agreement and semi-quantitatively also, in particular in the 5 orbital cases. So we use both techniques, but results do not depend on which technique is used in their main features. So there is then something else that happens in realistic models. So when you have bands which are not identical, is that in these plateaus, in these long zones where you have strong correlations, but not yet Mott insulators, correlations typically get orbitally selective. So there is a lot of work that has been done in this respect, both from the Rice group, from our groups in the last 10 or more years, and these orbital selective correlations in these zones of strong correlation dominated by Hund's coupling that are nowadays called Hund's metals are ubiquitous. Here we did some calculation for iron selenium and iron tellurium long ago, but these were very similar to the calculation by Ron Yu and Chimiao Si on the 111 and many others. And you will probably have seen this phase diagram with this Y-shaped phase diagram many times, and this is very universal. So it shows that if you have small Hund's coupling, you typically, as a function of the interaction strength, you have a metal to Mott insulator transition at some U, whereas really when Hund's coupling is sizable, you go through this phase, which corresponds to this Hund's metal phase, in which you have orbital selectivity. Be it in Adela's model, a sharp orbital selective Mott transition for some orbitals and not others, or a more gradual crossover, it's always there, and for the shape of the phase diagram is always the same. It's this Y shape so the zone widens with Hund's coupling. So there was a
Lucas, Lucas, do you mind if I just raise a question for the purpose of discussion? So in my mind, there's a confusion as to what the operational definition of Hund's metal is. Because when we did these calculations, one of the things we found is that there's a precursor to the orbital selective Mott phase. And that's the precursor regime where orbital selectivity appears. But at the same time, the lower Hubbard bands and upper Hubbard bands are still there. So I'm not sure what your operational definition of Hund's metal is, I guess.
Well, for me, as you said, the operational definition is given by the similarity between these phase diagrams. So here we are in idealized models. So clearly the onset, I think this is what you call the precursor. The onset of orbital selectivity really coincides sharply with an orbital selective Mott transition. When you have a more realistic calculation, clearly, as you see in both our calculations, it turns more into an avoided orbital selective Mott transition. You get a very heavy fermionic particle, but not a clear localization that then can happen further on, but the onset of selectivity is what is universal. Here is just the simplicity of the model that makes it coincide sharply with an orbital selective mode transition.
Right.
But in that, I don't think there is no real confusion. The confusion is more in the general definition of Hund's metals, and I agree with you, but that's a vast discussion that maybe we should have.
No, we should have probably a separate time, but I think the question of whether there's a lower Hubbard band and upper Hubbard bands has been the source of the confusion. You know, all our calculations that they are always there. So to me,
I think for me, there's no confusion. They are always there. They might be at a distance that you don't expect, because you have to renormalize also the mod excitations with J. But I don't think it's a general fact that they're not there. Of course, if you go at very low interaction strength, they might still overlap. That's a possibility, and that we saw that. But they're there.
Okay, thanks.
Okay, so I just wanted to quote a lot of work that has been done in theory with different techniques, and I think they all agree on the main facts that there is this selectivity of the correlations, both in models and in realistic calculations. It's really an outcome of the local many-body physics, and a lot of work has been done, but I think there is consensus in this respect. And also the fact that the XY orbital is always the most correlated one. It's also pretty well established. In particular, as far as iron selenium is concerned, I remember probably this Eichhorn et al. Was one of the first papers doing this with the MFT, and also of particular importance in the community played the role of these nature materials from the Rutgers group, in which there was a lot of comparison between the different materials. But I guess that in the end, the picture that comes out of this work from many groups is quite substantially in agreement on the main facts. So experiments also confirmed a lot of this physics. Now we'll go quickly through a few points. These were done for me. I mean, the correlation strength and the orbital selectivity increases with hole doping. So going from 6 towards 5 electrons in general in these calculations. And I think this is confirmed in experiments. So I'll show some results from the 1 to 2 family, which is the one that can be actually doped a lot and in a very detailed way with holes and electrons. But in here, it's one of our main comparisons experiment for the Sommerfeld coefficient, which tracks the strength of the correlations as a function of doping, and here also with some further substitution of the cations that increases the correlation in the 1 to 2 family, shoot up, whereas the DFT cannot follow. It's really flat, or more or less flat, whereas this is the outcome that you have with DFT plus slave spins. You have a very similar outcome with the MFT. And this requires no fine tuning. There's just one value of the interaction, and only the DFT is changing among these different compounds. So I think this really proves that Hund's coupling is at play, and there is a lot of physics due to correlations here, local correlations at play in these materials. And DFT is completely off. Another thing that I quote quickly is the fact that also the selectivity is increasing with hole doping, and this is the theory. This is what several estimates that we can have from experiments, and they also show a divergence of the selectivity between the different bands at the Fermi level and the different probes that are sensitive to the different bands with hole doping. So both the fact that the Hund's coupling is important and the selectivity is important, I think are very, very well confirmed by experiments. And these I will skip, but also the local moments that come out of the strong Hund's coupling are also seen in X-ray emission. Particularly for iron selenium, orbital selectivity was seen in a lot of ARPA's works. There is a nice work from still the Rutgers and group with Mingi. I think at that time she was probably in NZX Chen's group, but and there are other works. Here I quote some of the estimates of the mass enhancements for iron selenium and iron selenium tellurium, and they're very spread. So selectivity is there. And also there is a very nice work from the group of Seamus Davis with quasi-particle interference they showed that the spin fluctuation pairing can be reconciled with experiments only if one makes it orbitally selective and if one uses orbital selective differentiated coherence among the quasi-particles. So now let's go to our results. I'm showing here then again this renormalized simple DFT. And since these correlations are important as introduced from Hund's coupling and not just as a squeezing of the bands, and also they're highly non-intuitive, we did this calculation through Slay spins. And this is just to show that Slay spins on the traditional DFT are not able to reproduce in detail these bands. This is what we have. In particular, I would like to focus on the fact that here the XY band is in yellow and it's still at the Fermi level at gamma, whereas again, this is what I called your attention on before. I would like to see it sank. And these results are not very sensitive on the choice of these values. As long as we are beyond this crossover into the Hund's metal phase, you can vary this among some realistic values. You will still have the same topology of the bands, unless if you go to very unrealistic values. So we are pretty dissatisfied by this. And in fact, we try to move beyond the traditional DFT into what I will show you, hybrid functionals. Now, let me just focus also on the fact that if you look at the Fermi surfaces, the DFT Fermi surface is not cured of these problems, which are the fact that these pockets are too large compared to experiment. This is a scheme that is a little bit enhanced, but it's taken from experiments, and the experiments don't see these three pockets in gamma, and they see small, very elongated pockets at M. So what we have done is we have moved into the field of trying to understand how this Fermi pocket shrinking is done. And there's a lot of work that have been done again in the community, both evoking a dynamical mechanism, so a self-energy which is due to interband scattering, or also the fact that the DFT doesn't take into account correctly the short range interaction, for instance, through incorporating them through Fock. And this mechanism can both have a shrinking of the Fermi surface. In particular, only the second one seems to be giving correct shrinking for iron selenium. So this is interesting for us. But in other materials like the 111, they seem both to give satisfactory shrinking. But we want to really have it ab initio to not just the topology of the Fermi surfaces, but the sides of the Fermi surface, the pockets, but the whole band structure. So what we tried is follow a path which has been already explored of going beyond LDA or GGA. So there was some nice pioneering work from Van Schilgaarde Kotler with Jan Tomczak, in which they use quasi-particle self-consistent GW. Another from the group of Silke Biermann with Ambroise van Rockegem using screen exchange plus the MFT. And there is a recent also work from the George and Kotler group in analyzing the ARPES from lithium iron arsenic and establishing that DFT in the traditional LDA JJ form is not able to yield a correct description. What we want to stress is that, however, we can go beyond GGA. We do it with HSC, so the hybrid functional, and we obtain a corrected static reference Hamiltonian, so one body Hamiltonian, on which we can still include the local correlation from slave spins or the MFT and get a nice agreement in the end. So what we would like to show is that still, by doing the non-trivial decoupling of dynamical interaction, which are dependent on omega but not on k, once you have the right non-local static Hamiltonian, this yields good agreement with experiments. And indeed, So this is what we do. I can come back to the details of what is the hybrid functional, but this is one of our main results. You see that simply using, again, an interaction value, which is in the ballpark of what puts you right beyond the crossover into the Hund's metal phase. And simply using the standard parameters of the hybrid functional, we get this kind of band structure, which is in a very nice agreement with the experiments. It's not perfect, but it has indeed the sinking of the gamma band, of the XY band at gamma, has a nice shrinking and elongation of the pockets at M, and a nice match of the Fermi surfaces. And if we use this to predict whatever we can predict with this band structure, which in our technique with slave spins doesn't have the lifetime, so we can predict only things that do not depend on the lifetime, but with DMFT we are doing it, and we will be able to go beyond. One thing that can be reconciled with experiments is the specific heat Sommerfeld coefficient, so the slope of the linear part of the specific heat in temperature. This is too small compared to estimates that can be given from experiments, which are around 12 millijoule per mole Kelvin square. DFT alone, of course, gives it too small because you need renormalization, but renormalization on traditional DFT give a huge value, whereas using the fact that one band has sunk, this take away density of states at the Fermi level, and indeed HSE, so the hybrid functional plus slave spin, give a much better agreement with experiment. And then quite surprisingly, also the interband optical conductivity agrees very well with experiments. Here we are putting experiments in which we have subtracted the Drude peak, because again, the Drude peak needs the lifetime that we don't have with this technique. But okay, it was fitted by the experimentalists, and so it was easy to subtract it because we used the fit of the experimentalists to subtract the Drude peak, the narrow Drude peak, because there's typically two Drude peak used by people doing optics in fitting this data. So these experiments as what remains after subtracting the Drude peak. And here we have experiments from bulk, iron, selenium, and some thick films, which are very similar at low energy, and they differ a little bit, still maintaining some main features in energy at higher energies. And you see the renormalized PBA is really off. The slave spins on PBA are still pretty off, and slave spins with on top of hybrid functionals give a very nice agreement both of the features in energy and the overall magnitude of the spectrum. And we pushed it a little bit even too far, and we investigated the Seebeck coefficient, which as a first approximation can be calculated without taking into account relaxation time. Indeed, at least we saw that the other approximations give a completely wrong sign and behavior of the Seebeck coefficient, whereas at least our formulation gives a nice agreement and also a change of sign, more or less, in the temperature, which is comparable to what you find in experiments, even if probably, this is a super sensitive technique, and the fact that we, for instance, we don't include spin orbit coupling, it's of importance, since indeed by including ex post some on our renormalized band structure, some spin orbit coupling, we find that it can be tuned to agree a little better. So this, I will take it as a very general, not so specific prediction, but at least much better than the other approximations. So let me just show you something about the many-body physics, which I think it's very important, and which can be related to what we have just seen by the fact that we pretty stably, whatever the approximation we use, we place our compound in this zone just after the crossover into the Hund's metal. So we are close to the crossover, and indeed you can imagine that by applying pressure, you reduce the correlation strength compared to the hoppings, because you push the atoms closer to one another, and so you can get closer to this crossover. And indeed, there is one thing that I didn't mention. We always find where this crossover is positioned in all our simulation, a peak in the compressibility, in the electronic compressibility, which can be very important in screening, for instance, and in the even influencing the pairing mechanism, whatever the pairing mechanism might be. So it's the work of Pablo to show that if you put pressure on iron selenium, you can really bring the peak at realistic pressures at the realistic value of the interaction strength. Okay, so what I mean is that the compound is deep into the Hund's metal phase, and pressure brings it towards the crossover. And this is a nice agreement with the fact that under pressure the TC goes up. And Pablo has found this is in general the heat map of the compressibility, where you see you have a peak coming from a divergence that we find in all these calculations, even in models. So it's really something that I could explain. We have done a lot of work, but it can be explained, I mean, in such a short time. But it's really a feature of the many-body physics in these Hund's metals. This is the frontier is characterized by an increased compressibility, and if you move in doping towards alphaline, can even be a divergence. And the fact that you apply pressure, you bring the realistic, so this mustache towards the realistic values of the interactions, which are estimated, for instance, by CRPA. So this is what Pablo showed, the fact that when you apply pressure on and recalculate the DFT and keep the interaction, the interaction values constant and recalculate this compressibility with Slay spins, indeed you bring the mustache, this mustache of this peak of compressibility at the realistic values where the compound is. So basically, you can imagine that this enhancement of TC might be related to the increase of electronic compressibility. And this we see also in the comparison between bulk and monolayer. Yes, Chimiao?
It's already 25 minutes. Okay.
Okay, so I'm at the conclusions. So this is the last slide to show that we could discuss the same thing on the 111 family, and Pablo has calculated that also the TC in these families go nicely in agreement with the position of the peak and the Hund's metal crossover. And so let me just jump to the conclusions. I hope I could show you that we have improved agreement with experiments on the band structure of iron selenium, including correlations and using hybrid functionals, which includes screen Fock exchange, which is treated inaccurately by standard DFT. So this is needed, and that we can match several experiments nicely. And the important point is having this improved description from DFT and being in the Hund's metal zone. Otherwise, the bands wouldn't match at all. And there is an importance in being closer or further from this Hund's metal frontier, and maybe the fact that most of the compounds that we find with high TC are at or close to the Hund's metal frontier might be an indication that this frontier and the compressibility peak that you find there is a booster for superconductivity. So thank you for your attention.
Thank you, Luca. Yeah. Yeah. So question. Oh, so maybe we'll Ilya first.
Oh yes, okay. Luca, thanks very much for the nice talk. I have a question regarding the iron selenium. So I understood that when you compare, you always do the calculation for the tetragonal state. Yet very often when one compares with experiment, you look at the orthorhombic state. So I was just wondering whether, in your framework, is it possible, to do this DMFT calculation by assuming that you are in the orthorhombic ground state, and maybe even, put pneumaticity by hand and then see what's actually happening with the correlation in this pipe? Because what I noticed is that you still see 2 electron pockets at the endpoint in the tetragonal phase, and this is, I think, what is also experimentally seen. But we know that once we go into the orthorhombic state, there is this one pocket is essentially missing, and there is still a discussion whether it's basically because of the strong correlation, strong Z factor, whether it's maybe another effect of the nematicity. Could you maybe comment on this?
Yeah, sure. So indeed, we stuck to the tetragonal phase because the mechanism for nematicity is still subject to some debate. So it could be put by hand, but at the moment we don't have the possibility of having it spontaneously. So of course we could. Obviously, it doesn't make sense simply taking the orthorhombic Hamiltonian, because that has just a slight difference in the XZ, YZ due to the structural part. So we really need the feedback of the fact that nematicity is indeed a broken symmetry phase of electronic origin, and we don't have the mechanism for that arising spontaneously in our solution. So we could put it by hand, but then this would be subject to some other arbitrariness, because we would have then a driving field for this, and of course we didn't do it, but in principle we could.
Oh, Chimel? Yeah, I'm sorry, I'm muted.
I think Ming was Ming was.
Oh, Ming was first. Okay, Ming go. Yeah.
Thank you. Luca, thank you very much for this talk. I have two small questions. So one is that in your calculation where in iron selenium you're bringing down the XY whole band, does that change the filling of the XY orbital in this process? Or I don't know if that's even a relevant question to ask, bringing it closer to.
Well, it's not really a process, is what we find. And so you're asking me if in the end, the XY orbital is more or less populated than in the case of PB. I would say it's a little more populated, so it's a little further away from half filling compared to the PB. But I'm not sure this. I mean, this is just an outcome of the calculation. I couldn't really relate to anything in particular. Maybe also, this depends on the interaction strength. So what we checked is that our results are very stable when you move the U and the J in the range of realistic values, as long as you are in the Hund metal phase. Now the specific value of the population of the XY orbital might differ depending on how you move U and J, but in general, it's very comparable between the two cases. I would say slightly more populated in the HSC than the PB, but not the inverse. That's for sure.
I see. And if I can, thank you. So the second question is, in your comparison of the DMFT calculation and the Say boson calculation, where you're saying they're very consistent. So I just wonder, from an experimental perspective, how do we distinguish the two in the limit where the Z is very small in the DMFT, whereas in the Say boson is 0? So I don't know if there's a way to experimentally distinguish the two cases in that regime.
So what do you mean the two cases? What you mean is that in some cases, one technique gives you 0 and the other gives you a small z. That's what you're saying?
Yeah. So you had this slide where for the DMFT calculation, it goes down and it has a tail that goes on forever. And then there's the Say boson calculation that just goes to 0. So
well, no, I wouldn't say that's general. That might be a specific case. Maybe I showed in. Okay, let me try to share again, so you tell me which slide you're referring to. But in general, I wouldn't say that this is a difference. This is a difference between these two techniques. It really depends on the calculation. It depends if you have finite temperature too, because it's my understanding that the z equals 0 in these calculations can happen earlier if you raise the temperature, obviously, when you have a very small quasi-particle coherence. So in these calculations, so you're referring to this slide, right?
Yeah. So
okay. So I have to say two things. First, this is a comparison between the two techniques in the 3-orbital case. It's well known that, I mean, it should be clear, DMFT is more accurate in general. DMFT, it's slave spins, it's a cheaper, more simple approximation, which, however, gets more and more accurate with raising number of orbitals. So even if it gets also more computationally expensive, but this is also the case of the MFT. So in this 3-orbital comparison, you still see some differences in the curves, which are, let's say, the same color by color. But you shouldn't. These are just quantitative differences. Qualitatively, they do the same thing. So this doesn't go on forever. This vanishes here, whereas this vanishes here. It's just a quantitative difference, which is more enhanced in this 3-orbital case. In the 5-orbital case, it would be closer. But again, in general, the MFT it's a heavier but more accurate technique overall. So, but I never found a qualitative difference of importance.
Okay, thank you.
It's well.
Yeah, Luca. So nice talk. My question is connected to what I was referring to earlier, but also connected to Ming's question. Would you refer to this frontier? I think it's the same thing as what I was referring to, the precursor to the orbital selective mod exerting phase. And so I think Ron and I actually found that region first. And when we found it, we were looking for this sort of Hund's-driven versus Hubbard plus Hund's cooperating effect. And in our mind, the distinction between the two scenarios is whether there's a lower Hubbard bands and the upper Hubbard bands. If there is no lower and upper Hubbard bands, then charge is entirely coherent, spin may be incoherent. If there is lower and upper Hubbard bands, it means charge is as incoherent and localizing as spin is. And we always found that the lower Hubbard band, upper Hubbard bands exist. And by now, I think at least in Ming's data of FeSe, that's checked between theory and experiment. But my understanding that in FeSe, that's also found by ARCA. So to me, U and J Hunds are cooperating, and the lower Hubbard band is really very important, especially in terms of enforcing whether the XY orbital is close to half filling, closer to half filling to be strongly correlated. Because if you want get a mass enhancement, you have to move it closer, the entire filling to be closer to half filling. And the low Hubbard band is a very important feature for counting the filling. So I guess that's sort of overall comment. I don't know whether you agree or disagree, but the question to you
well,
is...
I agree on one point, which is important. I agree that there is some confusion on what we mean by Hund's method. That's why every time I give a talk, I try to say exactly what I mean. Probably we mean the same thing, and I think that it's not really possible to talk about effects of Hund's coupling without acknowledging that Hund's coupling is always a fraction of the Coulomb interaction. So I think U and J always are important together. We are highlighting what happens due to J in the sense that it's the value of J, it's tunes things in a very sensitive way. But it doesn't make sense of talking about J without talking about U. So I agree with you. It's just in this respect, I think we are talking about the same feature, this frontier, which is the onset of selectivity. Now, I think it becomes from a sharp frontier, it becomes a crossover, just because when you include all the off-diagonal hoppings that you have in a realistic Hamiltonian, you simply can't have a sharp transition, so you always have some residual coherence.
Yeah. So, but let me actually put a question to you. So I was a bit surprised when you said that the correlation is moving the XY or filling to be further away from half filling, because we always found the opposite.
Yeah, in fact, in our HSE calculation, it's slightly less correlated. So I think this is some mechanism that we stressed a lot and we isolated in these very first papers that we called orbital decoupling. So it looks that in this zone, once you have activated the selectivity, the main trigger of correlation is the proximity of the orbital to half filling. So one has to know what is the population of the orbital, and typically the hierarchy in the correlation strength goes exactly with the distance of each orbital from its own individual half filling. And that's why when Ming asked me, what do I find? Well, I was just quoting the fact, I don't know if here I have the data, that the XY orbital that we find running slave spin on top of the standard DFT is a little more correlated than what we find when we run it on top of the new HSE. Of course, this depends always on the value. We could go to a much higher value of U and find a much smaller value of the correlation strength. But overall, where we deem realistic, we find a little decorrelation of the XY compared to our standard calculation. But again, the important thing is what is the value of the Fermi velocity that you find in the end. And this
we should probably move on. But
yeah,
just
let's move on. Yeah,
just text 10 seconds. Do you find the low Hubbard band because ARPAS did, right? So the spectrum.
I think, okay, in slave spins, as you know, it's not immediate to get the spectral functions, but indeed we have I mean, you showed it nicely in your papers. There is a way to calculate the Green's function and show that there are features which are unfortunately very peaked. But in DMFT, we do find Hubbard bands. Yes.
Mm-hmm. Okay, thank you.
Yes. Thank you, Luca.
Thank you.
So can you unshare and then get Brian?
Yeah,
yeah, thank you, Brian. Thank you for your patience, Brian.
Sorry, Brian, for going over time.
No problem, no problem.
Okay,
I will show you how to
Brian,
go much more over time.
Great,
okay,
that's great, Brian. You can go, yeah.
You see the slides and the mouse?
Yeah, very nice.
Okay, great. All right, so thank you, organizers, for the invitation. And thanks for everyone out there listening. I will give a talk about related issues, iron, selenium, strong band normalization, and in a nutshell, the talk will really be about how do we get from this picture to this.